Good morning. In this lecture, we will discuss about a new topic which is called the number system. In this lecture, we will discuss mainly on the positional number system and the binary number system, and I will deal with the representation of binary number system and also about the binary arithmetic. As you know that the data and instructions are stored in any microcomputer using the digits 0 and 1, and this is called a binary number system. If the digits used in that number system is only 0 and 1, then it is called a binary number system. Before going to the details of the binary number system, let's discuss about what are the notions of a number system. That means a number system must consisting of a set of symbols for forming the numbers. So to form a number in a number system, there should be some set of symbols. As you know that in the case of a decimal number system, this is a very familiar one and commonly used one. The symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. are used as the symbols, and these symbols are known as digits in the decimal number system. And another notion of a number system is that after having a set of symbols for forming numbers, then we should have a set of rules which may be used to form numbers from these symbols. And assign values to these numbers. So the second notion of a number system is a set of rules to form numbers from these symbols and assign values to them. And third one is a set of rules for performing arithmetic operations in that number system. So these three are the notions of number system. So first one is there should be a set of symbols for forming the numbers. The second one is that there is a set of rules which may be used to form the numbers from these symbols and assign values to them, and there is another set of rules for performing arithmetic operations in this number system. If you consider our familiar decimal number system, we know that we already mentioned that the symbols 0, 1, 2, 3 up to 9 are the symbols used to form the numbers in the decimal number system, and these symbols are called digits in the decimal number system. And now you know that if you represent a number, let's say 157 in a decimal number system, then the positions of each digit are important, because the weight of the digit is represented by each digit is contained in the position of that digit in the number. Suppose you know that here this digit 7 is in the right first position from the right, or last position from the left, and it is in the position of ones, so it is having the weight of 10 raised to 0. Now if you consider the number 5, the digit 5, which is in the second position from the left, and which is having the weight of tens, that is, it is having the weight of 10 raised to 1. And now if you consider the first digit from the left, which is 1, and which is having the weight of hundreds, that is, it is having a weight of 10 raised to 2. So if you consider this decimal number system, the weight of each digit in that number actually depends on the relative position of that digit in the number. Such number systems are called a positional number system. So positional number system is the number system in which the weight of each digit depends on the each digit in the number depends on the relative position of the digit in the number. So such number systems are called a positional number system. Now if you consider all the number systems which are familiar to you, or which are at least hit you, that is decimal, binary, ternary, octal, hexadecimal, all are positional number systems, examples of positional number system. Now if you consider a number to, for example, the 157.65, let's say it's a decimal number system. It is actually a real number which is having both integer part and fractional part. We will discuss the floating points later in the case of a binary number. Just remember, just for an introduction, let's consider a real number in the decimal number system, and this number, if you consider the weight of each digit in this number, the first one digit, that is 1, will have the weight of 10 square or 10 raised to 2. The digit 5 has a weight of 10 raised to 1. The digit has a weight of 10 raised to 0, and definitely you know that the weight of this digit 6, that is first one after the decimal point, has a weight of 10 raised to minus 1 or 1 by 10, and 5 will have a weight of 10 raised to minus 2. So we can expand it in terms of this 10, that is 1 into 10 raised to 2 plus 5 into 10 raised to 1 plus 7 into 10 raised to 0 plus 6 into 10 raised to minus 1 plus 5 into 10 raised to minus 2. This will give 157.65. So here we are actually expanding this number in terms of the 10, which is actually the base of the number system. So the base actually represents the how much is the weight of the digit, or the weight of a digit is represented in terms of its base. So base for a decimal number system, base is 10. So in terms of the base, we can expand the number. So if you consider any number system, let's say it consisting of the integer part I1, I2, I3, etc. up to Ik, dot some fractional part consisting of the digits f1, f2, f3, etc. fn, then in terms of the base, this number can be expanded as, if you consider here the weight of 1 is 10 raised to 2, here the integer part has total of 3 digits, so the weight is 2. The first one is having a weight 2, so we can say that it is 3 minus 1. So if we consider like that, here this the I1, I2, I3, etc. Ik is the integer part. This integer part consisting of k digits. So the first one I1 will have a weight of k minus 1 power of its base. So if b is the base, then b raised to k minus 1 plus I2 into b raised to k minus 2 plus etc. Ik into b raised to 0 plus then the fractional part f1 into b raised to minus 1 plus f2 into b raised to minus 2 plus etc. fn into b raised to minus n. So this is the representation, expanded representation of any number in terms of its base. Here what we have to remember is that here b represents the base and k represents the number of digits in the integer part, n represents the number of digits in the fractional part. So now with all this introduction, let's move on to the binary number system. So you know that the data and instructions are stored in any microcomputer by using the binary number system. That is, the symbols used to form the numbers in this binary number system are 0 and 1. These two digits are called bits. In the case of decimal number system, the symbols from 0, 1, 2, etc. up to 9 are called the digits. Here it is called the bits. 0 and 1 is called the bits. So these bits are formed in different numbers in the binary number system. Now if you consider the 0 in the decimal number system, then equivalent binary number will be 0 itself. Now if you consider 1 in the decimal number system, the corresponding binary number is also 1. Now if you consider the 2 in the decimal number system, the equivalent or corresponding binary number is not 2, but it will be 10 that you have studied earlier, and that we will see how we can convert a decimal number into a binary number and how we can convert a binary number into a decimal number. So we are going to discuss in this lecture about the conversion of a binary number to a decimal number and a decimal number to a binary number. First of all, we will consider the conversion of a binary number to a decimal number. So binary to decimal conversion. For that we have to consider a binary number first. I am considering a binary number 1101. So it consisting of only zeros and 1, which is a binary number. So to convert it into decimal number, the easiest way is that represent this number in terms of its base. For a binary number, the base is 2. For a decimal number, the base is, you know that it is 10. So for a binary number, the base is 2. So each position, weight of each bit in this number will be represented in terms of the some powers of the base 2. So if you consider this first digit from the right, it is 1. So 1 can be, this one has a weight of 2 raised to 0 plus, then the next bit from the right side is 0. So 0 into 2 raised to 1 plus, then this 1 will have a weight of 2 raised to 2. So it is 1 into 2 raised to 2 and it is 3. So 1 into 2 raised to 3. That means the first bit from the right will have a weight of 2 raised to 0. The second bit from the right will have a weight of 2 raised to 1, and the third bit from the right will have a weight of 2 raised to 2, and the fourth bit from the right will have a weight of 2 raised to 3, and so on. So now if we do this calculation, you know that 2 raised to 0 is 1. So 1 into 1 is 1. Now here it is 2 raised to 2 is 2. 2 into 0 is 0. Now here 1 into 2 raised to 2 is 4. So it is 4, and it is 2 raised to 8. 3 is 8. So it is 1 into 8 is 8. So what we are having here is 1 plus 0 plus 4 plus 8, which is equal to 13. So this is the corresponding decimal number for the binary 1101. So this is the way we can convert a binary number to a decimal number. Just expand the number in terms of the base, or represent the number as the power of the base, and do the calculations. Then you will get the corresponding number, decimal number. Now another conversion method is there, which is called the double barrel method. In this method, what we have to do is that we have to double the bit on left, double the first bit from left, double the first bit from the left, then add the next, add the bit right to it, then again double the sum, and add the bit next to it, and then double it, and then add the bit which is on the right of it again, and do this procedure and until all the bits has been exhausted. That means, for example, if you consider this 1101, double the first step is double the first bit from the left. So this is here it is 1, so we have to double that. To double means multiply it by 2, then add the bit right to it. So this is the number or bit right to it, then double this sum, then add the number right to the next. So it is, that is 0, then again double the sum, then add the number right to it, that is plus 1. So now all the number has been taken or exhausted, so no number, so there is no need to double it again. If there is any number, write to it after taking the sum, then we have to double the sum and add that number to the sum after getting the doubling. So now if we do this calculation, here it is 1 into 2 is 2, 2 plus 1 is 3, 3 into 2 is 6, 6 plus 0 is 6 itself, 6 into 2 is 12, 12 plus 1 is 13. So this method is called the double babel method. So you can obtain, so this is a binary number and corresponding decimal number is this one. So either of these method, that is just by representing the weight of each digit in terms of its base and expand the thing and do the calculations, we will obtain the corresponding decimal number, or use the double babel method. That means double the first number from the left and add the bit right to it, then this sum is doubled and then add the next right bit to it and then again sum it, and the procedure is continued until all the digits has been exhausted. So that is called the double babel method. So we can use either of these method to convert a binary number to a corresponding decimal number. Now we have to discuss about the conversion of a decimal number to a binary number. How we can convert a decimal number to a binary number. So we have to discuss decimal to binary conversion. For that, just what we will do here is that we will repeatedly divide the number by 2. That means suppose we are having a number, say some integer x or x, and divide this number by 2, and we will get a remainder as some quotient and a remainder, some quotient, let's say y, and a remainder will be either 0 or 1. So note down that remainder, let it be r1. R1 will be either 0 or 1. Then again divide the quotient by 2, which actually gives number of 4s in the number. Anyway, that will give a quotient again, some y1, y2, which is again still we will have a quotient of remainder of 0 or 1, let it be r2. Now again divide it by 2, then we will have a quotient y3 and we will get a remainder r3, and this procedure is continued until the quotient become 0 and we will get some remainder Ri, which is also either 0 or 1. So now write these reminders in the reverse order, that is from Ri to R3, R2, R1 will be the corresponding binary number of the decimal number. So for example, if you consider the decimal number 44, now I want to convert this 44 into a decimal number to a binary number. For that, let's divide this 44 by 2 first. The quotient will be 22 and the remainder is 0, that I am putting here. Now again divide it by 2, so the quotient will be 11 and the remainder is again 0. Now repeat the division by 2, we will get quotient as 5 and the remainder as 1. Divide by 2, we will get a quotient as 2 and the remainder as 1. Again divide by 2, we will get a quotient as 1 and the remainder as 0. Again divide by 2, we will get quotient as 0 and the remainder as 1. Now arrange these reminders in the reverse order, that is from bottom to up. That is, the first remainder will be 1, then 0, then 1, 1, 0, 0 is the corresponding binary number for 44. Now if you have any doubt in this one, let's convert this 101100 to the corresponding decimal number. For that, we have to represent it in terms of the binary weight or the base of the number, or we can use the double bubble method. I am using the expanded form in terms of the power of the base. So here the first digit I am taking from the right, which is 0. 0 will have a base weight of 2 raised to 0. Then the next 0 will have a weight of 2 raised to 1. Then the next number is 1 into 2 raised to 2. Then next number is 1 into 2 raised to 3. The next number is 0 into 2 raised to 4. And the next number is 1 into 2 raised to 5. Now this is 0, this is 0 and this is 0. What remains is, here it is 4, here it is 8 and here it is 32. 2 raised to 5 is 32. Now 32 plus 8 is 40, 40 plus 4 is 44. So it is the corresponding decimal. So the binary decimal to binary conversion is done in this way. Divide the number by 2 and note down the remainder. Then repeat the division by 2 by noting all the remainders in each step of the division, and this division is continued until the quotient becomes 0. Now arrange the reminders in the reverse order will give the corresponding decimal number of the corresponding binary number of the required decimal number. So that's all about the binary to decimal conversion and decimal to binary conversion. Now we have to discuss about the representation of numbers like integers, real numbers, fractional numbers, etc. That we will discuss in the next video. Thank you.